if you remember, yesterday afternoon, I had gotten about 3/4 of the way through the story of PageRank, and I left one very interesting topic out, which is displayed here: the matter of link spam and how you combat it. Well, let's see. Since I'm running a little bit behind where I want it to be, I've decided I would like to move the slide set 6, which is the clustering, to the end. It's an important topic, but it's also kind of classical in the sense that most of these ideas were developed before most of the audience was born. Anyway, and there are lots of places you can learn about that, whereas the 7th and 8th slides are things that are kind of new, and I think, anyway, I don't want to waste a lot of time explaining. If I have to cut something out, I'd rather cut something out of the clustering. Okay, so all right, so let's talk about link spam again. Remember, the whole idea behind PageRank was to deal with the spammer who would fake what was on his page by putting words that really didn't describe what he wanted to sell you, let's say, in the hopes that you would go to his page looking for something entirely different. Because it's no harm to him. I mean, it costs him some tiny fraction of something to serve the page to you, and if you just if you happen to buy something from him, that's great. If not, he doesn't care that you didn't get what you were looking for. Anyway, the PageRank helps defend against pages like this because they're not important pages. They don't have a very high page rank. They're not going to be shown to you in the top 10. But there's there's another trick which Google used right from the start, which is very important, and that is Google believes what people say about you, not what you say about yourself. So you can put all the words you want on your page. What they're really looking for is what appears in the anchor text that important pages have in their anchor text leading to you. Okay, that's very unlikely to be a lie. And you can't control that because even if you make up a page that links to yourself and lies about what you are, that page will not be important, so Google will just not believe what it says. At any rate, the war wasn't over. The spammers simply had to do something more complicated, and so the idea of link spam was invented, and link spam is implemented by very large collections of pages, and I'll show you at least the simplest form of a spam farm. And its goal again is to just increase the page rank of some particular page that you want to give a high page rank to, in the hopes that that page will be selected by Google to put into the top 10. Okay, so first of all, if I'm a spammer, I see the web as divided into 3 pieces. First is my own pages, the things I can control. Okay, obviously the things that are on my server. The third thing are the inaccessible pages, the things that I just cannot control. But in the middle are accessible pages that I don't own, but I have the ability to manipulate in some way. And a typical way to do this is any page that allows you to put comments on the page if you, let's say, join some society. So you join the society, and in answer to some question you say, I have just the answer you need for that question. And then you put a link to your spam page. Okay. And you don't care that it's not really answering the question. All you want is for Google to think that there's a link to, or to know that there's a link to your page. And that's the whole game, folks. Okay, it's sorry. And by the way, you can do all you want building a spam farm. If nothing from the outside links to it, no search engine's going to find you. So it's as if you don't exist. So you have to have these accessible pages, and you have to manipulate them in order to get any page rank at all, and in order to be even known to a search engine. Okay, so again, the goal is there's some page T, which we'll call the target page, and that's the page whose page rank you want to make as large as possible. And so you're going to use the accessible pages to put as many links as you can to page T. Okay, and but in addition to that, you're going to build a spam farm which will consist typically of millions of pages. And the spam farm actually does two things. First, it actually amplifies the page rank that T gets from the outside. That is, the accessible pages give T some page rank. And the spam farm sort of recirculates it and accumulates the page rank. If you didn't have a taxation scheme, essentially because it's a spider trap, eventually all page rank would go into to this target page T. But it's because of taxation, you can't amplify it infinitely, but you can amplify it significantly. And I'm going to show you just how well you can do. But there's another thing, which is because your spam farm is so large, it represents some decent fraction of the web. Let's say if the web is, I don't know, Google maybe crawls 1 trillion pages. If you have a spam farm of 1 million pages, you're actually 1/1,000,000th of the web, as far as Google can see, and you therefore get 1/1,000,000th of the taxation, and that's a lot. Remember, the sum of the page ranks is supposed to be 1, because it's supposed to represent the probability that a random walker lands on your page, but. So if you can give page rank of 1/1,000,000th to your target page, that's actually very good, right? There can't be more than 1 million pages in the entire web that have a higher page rank, right? All right. So anyway, okay. So here's the web as far as the spam farmer is concerned. Okay, they're inaccessible stuff. You don't really care what goes on there, except you can be pretty sure that Google starts crawling from there, but will eventually find one of the accessible pages. You've put as many links as you can from the accessible pages to page T, and then. I don't know if you can see that, but the idea is you have M farm pages, where again, think of M as 1 million, and T links to every one of these 1 million pages, and every one of the 1 million pages links back to T. And that's how you're going to recirculate the page, or whatever page rank comes into T. And notice the thing on the right is a spider trap. Once page rank gets in there, it can't get out. Okay, the spam farm is recirculating it again. And the reason you use a large number of farm pages is to get as big a share of the taxation as you possibly can. Okay, so. Let's see. So I want to do the math. I want to. Okay. I'm going to suppose that the page rank that comes in to T from the accessible pages is some number X. Okay. I don't know what X is, but it's not 0. Then page T is going to have some page rank. I'm going to call it Y. I don't know what Y is yet. I'm going to actually, all of the work I'm going to do is to figure out what Y is. and in particular to show you that it's going to be pretty high. Now, I'm assuming the taxation rate is 1 minus beta. You can think of beta as 0.85. That's a common choice. So, in other words, you get to keep 85% of your page rank for the next round. 15% of it is taxed away. Okay. Now,
one question. So, is it that in this particular case, all of the farm members and the T would have the same page rank?
No.
No?
No, because in fact, the farm pages only get 1/nth of T's page rank, whereas T gets all of theirs. So T will have roughly m times as much page rank as each farm page.
So no
yeah, yeah. I guess the farm. I'm sorry.
they're not interconnected
They are not
with each other.
No, no.
We are not from the accessible set.
Yeah. Roughly, let's put it this way: the page rank of T is roughly equal to the sum of the. I think it's actually equal to the page ranks of the sum of the page ranks of all the other farm
So
pages.
they have to be careful not to link to each other, then not to lose the links.
Yeah, right. You could have a more complex structure. Oh, and by the way, if you're planning to build a spam farm and you build it this way, Google will notice it really quickly, okay, and get rid of you. So you have to do something a little bit more sophisticated. So maybe you will to put some links be among the M pages or something like that to make it look a little different. But let's not worry about that. Okay, so let's see. Okay, I claim that the rank of a farm page, let's see. Okay, beta y divided by m, that's what each farm page gets from T at the next round. Remember, beta is the fraction of your page rank that you keep, or rather that you distribute to your successors. So T gets to keep beta y, that's like 0.85 y, let's say. And each of the m pages in the farm get 1/nth of that, so that's why I divide by m. And then the farm page also gets the tax divided by each farm page gets 1 minus beta, that's the fraction that's taxed away, divided by the total number of pages on the web, which is n. Okay. So probably the first term is the dominant one because m is going to be much, much less than n. Okay. Okay. Now, I can ask okay, so now I want to solve for the page rank of T, which is y. Well, first of all, the first term is x. That's what the page rank that's fed in from the accessible pages. Okay. Now, what I've circled there is what I gave you on the previous slide, which is the formula that gives you the page rank of each farm page. Well, I have to multiply that by m because there are m farm pages, but then I also multiply by beta because the farm pages only retain fraction beta. Again, think of it as 0.85 or 85% of their total page rank. Okay. And then the last thing is just T's tax share. T is just one page. We're going to neglect that because it's tiny. Okay, but I think you can see now we have y in terms of a formula that involves x and y. So if you slog it around a little bit, well, I guess this is just expanding out the parentheses. Again, you trust me. What you get is y is x divided by 1 minus beta squared plus a constant c, which is about a half, since beta is close to 1, of m over n. Okay, so, so what you have is, again, this is the division by 1 minus beta squared. Again, think of it, if beta is 0.85, 1 minus beta squared is about 0.3. So you're amplifying, so you're dividing x by a fraction that's considerably less than 1. So the first term is much bigger than x. You've actually amplified.
3 times.
Roughly 3x. But in addition, you've got this term, which can often be the big win, which is, again, c is about a half. So you know, if you're a millionth of the web, you get about the page rank of T is already 1 over 2 million, plus whatever you can accumulate by amplifying what comes in from the outside. Okay? Well, I guess this is sort of what I said. If you assume beta is 0.85, and that's a reasonable assumption, 1 over 1 minus beta squared is 3.6. So you're multiplying by 3.5. And again, and then there's this term, which I can't really compare it because it just depends upon how energetic you are, how big you're willing to make M, and of course how big Google is willing to make N, how many pages they're willing to crawl. Okay. So anyway, if you want to go into the spam business, that's how you do it, roughly. But now I want to talk about, okay, so how do we detect, or we as Google, let's say as Google or Bing, how are we going to detect whether a page is in fact a target page for some spam farm? Where is it getting its page rank from something, from some illegitimate source? So the first idea is you can talk about what's called the trust rank, which is a topic-specific page rank where the teleport set is a set of trusted pages, and where you find your trusted pages, again, that's tricky. We'll talk about it a little bit, but assuming that you can that you can identify a reasonably broad set of trusted pages, you can compute trust rank. And then you can define the spam mass to be the page rank minus the trust rank divided by the page rank. In other words, what fraction of your page rank comes from trusted sources? Well, in particular, the spam mass will be high if most of your page rank comes from untrusted sources. And that means you may be part of a spam farm. Okay, so how do you pick a trusted set? Okay, well, okay. One thing is you probably have to look at the pages before you trust them. Okay, now there's this assumption that is probably pretty reasonable, which is, if a page itself is trustworthy, it's not going to link to untrustworthy pages. And probably it won't link to pages that themselves link to untrustworthy pages, but the further away you get from a trusted page, the more likely it is that you reach an untrusted page. That's why what the topic-sensitive page rank idea is about. You let the crawlers crawl for a certain distance, but the probability of that crawling really far away from one of your target page, one of the teleport set pages is kind of small. So the walkers are going to tend to be in the trusted area. The trouble is, I mean, if I just found 10 pages that I knew I trusted. And and made them my teleport set, I probably wouldn't get everywhere in the world that I needed to get. Okay, I need a much larger set than, say, 10 pages. Okay, so I'll just mention, a couple of things. One thing you can do is trust the really high page rank pages. The reason is, while you can boost the page rank of your target page if you're a spam farmer, you can't do that. You can't do it too much. You can do it enough that that page will be the answer to particular queries, but you can't get into the top 1,000 pages by page rank. I mean, those are just going to be occupied by Google and Yahoo and Amazon and IBM and Microsoft and things like that. Okay, so you can just say, I'll trust the top 1,000 pages or top 10,000 pages or something. I think I mentioned this before. If you take a domain that has where you have to apply to become a member of it, like .edu, then you can be pretty sure that there are no spam farmers that have set up that look like educational institutions. So that's another way to do it. Anyway, okay, that looks like I've sort of gone all the way through the woods on this. But
is there some other attempts to solve it? For example, because what I understand the problem with this spam farms is that Google or the page rank gives equal share of taxation to all the nodes. That's why this million.
Well, no, I doubt very much that is true. I'm sure, in fact, that Google only gives share of taxation to some trusted nodes. I don't know exactly what their definition of trust is, but I'm sure it's not everybody gets an equal.
But in that case, then this part of this formula would be, go to zero. This m over n.
That's right, and that's one of the ways Google combats
exactly.
the notion of a spam farm, because the spam farm does rely on, well, sorry, it doesn't. I mean, it still can. That's only one component, right? But so yes, if the taxation is distributed evenly to all pages, then the spam farm gets a share of taxation. Again, I doubt that that's true, but even without that, you still do get the amplification of whatever page rank you can manage to extract by taking advantage of accessible pages.
Yeah, but then it's all accessible pages. Then you cannot do much with the farm itself. Right.
No, but the farm still amplifies what you get from the accessible pages. Remember this, that's sort of the factor of 3.6.
Just think of the random walkers, when whatever comes into this sort of a farm,
Yeah.
if you don't get an extra taxation, you cannot do much more than that. Right?
No, because again, the farm is a spider trap.
Yeah.
When walkers come in, they'll stay there, and if the taxation was zero, eventually all the walkers would wind up in the spam farm, and...
No, so that, I mean,
but,
the taxation is fine, but you shouldn't get the tax from the authority back.
That's right. You can be pretty sure that they actually don't these days.
Okay, so
but you still have this phenomenon that walkers come in from the accessible pages, they'll walk around the farm for a little while, then they disappear, they get taxed away. But they don't get taxed away immediately, and that's what that factor of, say, 3.6 represents, is the fact that they will tend to wander around, so that a walker that came in 5 steps ago has some reasonable chance of still being there and adding to T's page rank.
Can you just comment, if you have like a minute, what would be the consequences if say Google was using Kleinberg's hubs and authorities? Would it be the same problems, or they would
I guess the spam farm would have to look a little bit different. but yeah, you could build up two kinds of page, the hubbiness and authority. I'm pretty sure you could do that.
So how Google in the end is going to detect link spam?
Okay, well, again, by using a topic-sensitive page rank, a scheme, it probably doesn't have to.
I see.
Okay, because it makes it gives very little page rank to a spam farm on the assumption that you don't have reliable pages. Like, you don't want the Stanford homepage linking to a spam farm.
Yeah. Okay.
Okay.
So that's the point.
And you have to sort of count on that.
The
That's not.
accessible pages that we talk about here,
Yeah.
that
They're-
point to a spam farm, these will have low rank somehow.
Yeah, right. The accessible pages, things like blogs. Yeah, you want to make sure that they're pretty far from a trusted page because they are not trusted. They are in fact subjected to the opportunities that spam farmers have. Let's see. So, again, it wouldn't surprise me if you, let's say, if Google is also looking for structures, right? I mean, first of all, you have to have a site or a small number of sites that have millions of pages. They have to be all interconnected. And there has to be there's got to be a lot of regularity to them. And, there are things you can do like looking at the content of the pages. As I said, you put links on the page. Well, are you going to have pages that have just links and nothing else? Or do you want to have text? If you have just links and nothing else, that itself looks very suspicious. Exactly. If you put if you put text there, and you want to have 1 million pages, you can't actually type 1 million pages. You have to have some mechanical way of getting them so they all look the same or they all look random or something like this. If you remember, we talked a little bit about this when
Google has the ability also to look at the graph. They can analyze the graph. They have the ability to.
Well, they could certainly, again, that's why I said if you really want to go into the spam farm business, don't copy what I just showed you exactly. Because that is certainly an easy subgraph to look for. You got to make it look somewhat different, but you can also see that you don't have to make it look too different before it will fail to match a template. Okay. Okay. So anything else before we leave this topic? Okay. So let me. Okay. Yeah. Again, so let me skip ahead, talk about graph algorithms. Again, there are a lot of very interesting new ideas that have come out in the social networking area. I want to just talk about 3 things, each of which I think has a bit of interest to it. I hope you'll find it has a bit of interest. One is finding communities. Communities are subsets of nodes that are dense in edges. Okay, if you belong to a club, you probably friend a lot of members of the club, that kind of thing. Another is counting triangles. This turns out to be a very interesting problem. First of all, there's a reason to count triangles in a social network, which is an old community tends to have a lot of triangles. If you think of them as triangles as 3 people that mutually friend each other. As a community gets older, people meet the other members of the community. If A is friends with B and C are going to meet eventually and may well become friends. So the triangles tend to get filled in. In a young community, one that's still growing, you tend to have fewer triangles. It's less dense in triangles. And why might I care? Well, why? I might want to be able to distinguish an old community from a young community, because old communities are not going to grow anymore. Young communities are going to grow. They're the kinds of things you might want to jump into or try to influence in some way. And then I want to talk about estimating neighborhood sizes. This turns out to be an interesting application of the Flageolet-Martin algorithm that, again, has nothing to do with streams. And okay, why do I care about neighborhood sizes? Well, again, if I'm a node in a social network, the size of my neighborhood going out, friends of friends of friends, the size of that neighborhood sort of says how important I am in the network, right? You give me a free iPad and I'll tell lots of people about it, okay? Whereas if I have very few friends, if my neighborhood is small, you don't want to waste your money giving me an iPad. And I said, yeah, you can laugh, but I mean, that's what marketing has been reduced to these days. I don't know. Okay, so anyway, let's talk a little bit about, okay, first of all, social network graphs, you see them in a lot of places. Obviously, the Facebook Friends graph is probably, if you think of that as the social network graph, you're probably not too far off. But first of all, it's huge. It's got 1 billion nodes, and there are hundreds of billions of edges. And I assume everybody understands. The Facebook's subscribers are the nodes, and the edges mean subscribers that are friends. Twitter followers, you've got about 300 million nodes these days. Again, that says a subscriber. And now this is a directed graph, actually, because if A can follow B and B doesn't have to follow A, but if A follows B, then we'll draw an arc from A to B. And again, there are hundreds of billions of arcs. There are other networks that have the same structure. And I'll tell you, what, a social network graph is not a random graph by any means. Okay. For example, telephone calls. The nodes are the phone numbers, and there's an arc from A to B if A has ever called B or has called B in the past month or something like that. Email, same idea. Email addresses are the nodes. If one email address has emailed a second email address, then we'll draw an arc. There are some social networks that have 2 or more kinds of nodes. So, for example, the Wikipedia articles and the editors of those articles can be nodes, and there's an edge between an article and an editor if that editor has done any work on that article. Similarly, you can have things like co-authorship. Nodes can be journal papers and authors of those papers, and there's an edge connecting each paper node to the author nodes that are authors of that paper. Okay, so anyway, the thing that makes these graphs just different from the classical Erdős random graph theory is that there is community structure, and you can think of it this way: if I have an edge from A, essentially the transitivity is going to give you a lot more edges than you would expect. So if there's an edge from A to B, there's also an edge from B to C. It's more likely than average that there will be an edge from A to C. Okay, and that's the real property of a social network graph. So I want to talk about the problem of partitioning a social network into disjoint communities. This is, by the way, and I should say, again, if you look at the MMDS book, we talk about the harder problem of finding non-disjoint communities, because you may be a member of the chess club, so you have links to members of the chess club, and you're also I don't know, you're fellow the people you graduated high school with. You're also part of that community, so you could be. Communities don't necessarily neatly partition a social network, but the first thing you might talk about is how could I partition a social network graph into communities, things that are in a sense locally dense in edges, and so that's what I'm going to talk about here. And there's a concept that refers to edges, or the betweenness of an edge is, well, it's defined here. It's the number of pairs of nodes whose shortest path goes through that edge E. So an edge E that connects a lot of guys here to a lot of guys here will have a high betweenness, and therefore will probably not be part of either of their communities. Okay, so what we're actually going to wind up doing is finding the nodes that have the highest betweenness and clipping them in order to separate the network into communities. And you just order the edges by highest betweenness first, and you keep deleting edges until you're sort of satisfied that you've broken the graph into communities. Well, I need to be a little bit more precise because there might not be just one shortest path between two nodes in A and B. There could be really any number of them, and the edge E might be on some but not all. So we're going to credit E with the fraction of the shortest paths from A to B that do go through E, through the edge E. And then, of course, we're going to add up this fraction for all pairs of nodes A and B, and that becomes the betweenness of E. Okay, and then as I said, you want to eliminate the edges of the highest betweenness, and that's going to break things into communities. Okay, so here's a social network, not a very big one, obviously. I can't give you a really big example. I claim that the betweenness of the edge BD is 12. Why? Because it appears on every shortest path from A, B, or C to any of D, E, F, and G. And that's, of course, the edge of highest betweenness, and it should be pretty obvious that when I clip BD, I've already separated this graph into two natural communities. Now look at GF down there. Its betweenness, I claim, is only 1. Okay, it's obviously on the only shortest path from G to F, but every other pair of nodes has all its shortest paths not going through the edge GF. So GF has the least betweenness. You're least likely to want to eliminate the edge GF to separate communities. So there's an algorithm that was developed here called Girvan-Newman. And the idea is to calculate the betweenness. It takes the time it takes is nodes times edges, which, if you think about it, is a lot better than the obvious algorithms, which would be node squared times the time it takes to find all of the shortest paths between those two nodes. So the first thing we're going to do is, first of all, we'll do a breadth first search from every node in the graph. Now, I'm going to talk about only one such breadth first search. So the whole algorithm involves repeating what I tell you for every node in the graph as the root of this breadth first search. Okay. Then we'll do a top-down pass in which we label the nodes only, not the edges, to count the number of shortest paths that go from the root node to that node. Okay. And that's easy. That's really just summing the labels of the parents. Okay. Then the tricky part is we're going to then do a bottom-up pass in which we label both nodes and edges. And again, the objective is that the label of a node will be the fraction of shortest paths going from the root of this breadth first search to that node or anything below it. And for edges, it's the same thing, but the path goes through that edge. Okay. Well, again, once I do this for every node as root, then I can sum the labels of the edges that I get in the bottom-up pass. I sum over all of these breadth first searches the label of the edge in that breadth first search. And then I have to divide by 2 because I don't want to double count. That is, you'll have a shortest path. If the shortest path from A to B will be counted once with B as the root, another time with A as the root. So I just divide by 2. Okay, so let's see. Here's in the corner is the graph that I started with. In this case, I'm using E as the root, and this is the breadth first presentation of that graph. It's really just the graph rotated a little bit, but at the right there is my breadth first search. Now, I'm going to start. Okay, how many shortest paths are there from E to E? Obviously, just 1. To D and F, again, well, to any node, the number of shortest paths from E to that node is the sum of the number of shortest paths from E to the parents of that node. So the only place where this becomes interesting is in G, where it has 2 parents in the breadth first presentation, D and F. So you sum the 1 and the 1, and that gives you 2. Well, anyway, B has only D as a parent, so it just gets 1. A and C each have B as a parent only, so they each get 1. So everybody sort of gets 1 in this case, except for that node G. Not very interesting, obviously. Could be much more complicated if more nodes had multiple parents. Okay, so now we got to do the bottom up. So I'm going to leave in black the top-down counts. By the way, the only time I need these top-down counts are when I have to divide the when I have to figure out the share of shortest paths going through an edge. In particular, I know that there are 2 shortest paths from E to G, but how many of them go through DG and how many of them go through FG? Well, the way I tell is by looking at the labels D and F. Okay, and what that says is, in that case, is that they divide half and half. So half will go through DG, and half will go through FG. Now, in this case, where the label of bottom-up label of G will be only 1. If G were not a leaf, there might be many there might be some big part of the graph accessible from G, so there might be many, many shortest paths going through G, from E through G to something else. But because D and F have equal labels, I know that half of them go through D, half of them go through F. And therefore half of them go through the DG, and half of them go through FG. So let's see how this thing works. Okay, first of all leaves get label 1. Right? Because we know that all shortest paths from E to some leaf go through that leaf. And no other shortest paths go through that leaf. Because there's nothing below. And remember, the red label that we're computing bottom up is the share of shortest paths from the root to a node or anything below. But since leaves don't have anything below, it'll just be 1. Now, edges in general, working bottom up, get their share of the red label of their children. In this case, B has only one child, A, and A has only one parent, B, so B gets the full share of A's label, which is 1. So it's the edge BA gets the label, the full share of A, which is 1. The edge BC gets the full share of C's label, which is again 1. And that says that there's exactly one shortest path going from E through somewhere below the edge BA. And in that case, it can only go to A. So that's in fact right, that there is only one such path. Now, as I'm working bottom up, if I come to an interior node, if I have all of my edges labeled, the edges below it labeled, I take the sum of the edge labels, because certainly anything that's going to go through the edge BA has to go through B, and anything that's going to go through BC also has to go through B. And then I add 1, because B is itself a node, and therefore the target of has a shortest path from E to B. You know that's not going to go anywhere below. So in this case, the label of B would be 3. Now, again, working up, we split the labels of the nodes get shared among all the edges to parents. In the case of the edge D to B, it gets the full share of B's label, so it gets a label 3. In the case of the edges into G, they each get a half the label of the red label of G, saying half of a shortest path goes through DG, half goes through FG. And again, the reason it's split half-half is because the black labels of D and F are equal. If the black label of D had been 5 and the black label of F had been 3, then the edge DG would get 5/8 as its label. Well, then moving up again to the next level of nodes, again you sum the labels of the edges below and add 1. So it's 3 plus 0.5 plus 1 is 4.5. That's how I get the level of D. For F, again, it's 0.5 plus 1 is 1.5. And then those labels propagate to the edges above because there's no splitting. And then finally, the label of E is going to be 7. That turns out to be irrelevant because we really only need the edges labeled. So I just wanted to let's just check this thing out, right? The edge ED gets labeled 4.5, so there should be 4.5 shortest paths from E to other nodes. Okay, well, from E to A, B, C, or D, the edge ED is on all the shortest paths. So that counts 4. And in addition, the edge ED is on 1/2 of the 2 shortest paths from E to G. right? Because you can go EDG or EFG, it's the same distance. So that accounts for the half in the label. And then it's not at all on the shortest paths from E to F. So that contribution is 0. So at least, as I said, it's a sanity check. At least one case checks out. Okay, so here's what the Girvan-Newman algorithm gives you for if you ran it with every node as the root. So if I delete the edge with the most betweenness, that sort of makes sense, right? If I want to delete the highest betweenness edges that remain, I would do this. And I claim that sort of makes sense. Why is B separated from A and C, but not A separated from B and C, or so on? The theory might be that, well, B is somehow a traitor to the ABC community because it's also friends with D, whereas A and C remain only within their group of friends. Okay. Well, let's see. Should we take a 10-minute break?
Yeah, sure.
and
We'll do that.
and come back?